Hi everyone, today I will introduce ESP WebRTC, a WebRTC realization on ESP32 service platform. First, let me introduce myself. My name is Tian Haibo. I work in Expressive Media Solution team, and my main job includes design and maintain media framework, media protocols, also develop some media solutions. My talk will include four parts. The first part, WebRTC basics. Then I will introduce ESP WebRTC. The third, I will compare ESP WebRTC with our ESP RTC. Finally, I will also share some debug tips. Firstly, let me introduce WebRTC. WebRTC is a big protocol and it contains many RFC docs. Firstly, let me introduce some key terms about it. RTC, real-time communication, SDP, session description protocol, DTLS, diagram transport layer security, RTP, real-time transport protocol, RTCP, real-time transport control protocol, SRTP, Circuit Real-Time Transport Protocol, ICTP, Stream Control Transmission Protocol, ICE, Interactive Connectivity Establishment. Turn means traversal using relay and stun session traversal utilities for NIT. Firstly, we will give overview for WebRTC. We mainly talk about its realization on browsers. WebRTC provides easy means to develop web real-time communication applications. It's internally supported by modern browsers, so you needn't install any plugins. Basically, WebRTC consisted by three parts: peer connection, media stream, and signaling. Media stream and peer connection is internally supported by browser, but signaling it needs a user to implement it. Peer connection. Its function includes the following. It is used to build up connections based on ICE. Also, it negotiates for media capabilities and decide rules such as which peer act as controlling, which one act as controlled. In the user scenarios, we also call it as caller or calling. It's another rule function is used to send and receive media data, including audio data and video data. Also, user can send user data through peer connections. It's realized by peer connection data channel. Also, it maintains connection with the server and another peers. Media stream provide high-level APIs to easily do capture and playback. It contains following parts: media capture. Media capture is consisted by audio capture and video capture. Media playback also it includes audio playback and video playback. Audio and video engines. It includes audio codecs, video codecs, audio processing like auto echo cancellation, noise suppression. Video engine contains maybe synchronization and image enhancement. They also include network adaptation functions. It is realized by JIT-buffer. Both audio engine and video engine contain it. Another part is signaling. Signaling is not a part of WebRTC core, but user can implement it through its own protocols, such as MQTT WebSocket. Its main function is used to exchange SDP, ICE candidates, peer certificate debt between peers. Following diagram shows that SDP exchange process. Both peers send their SDP to the synchronous server. When one connects in the SDP, the synchronous server will answer peers' SDP so that they can use it to build connections. This part will introduce ESP WebITC. Quite similar to brothers, ESP WebITC provide a complete solutions for WebITC implementation. It consists following part: a WebRTC core and a media core. WebRTC core consists ESP peer and ESP signaling. Media core consists by ESP capture and ESP player. ESP peer. ESP peer provide an interface for peer connection realizations. User can implement their own peer connections. They also provide some default implementation named peer default for convenient use. This part shows that the interface. Maybe there are two ESP peer implementation like peer default and Amazon KVS peer realizations. The peer default support following features and also it has some benefits. It supports STARM protocol, turn relay, SDP best interface, and SDP integration, IPv4 support. We cannot support IPv6 currently, but we will try to support it in the near future. It supports multiplexing on a single UDP port. Currently, it supports retransmission using SCDP NAC. It also supports controlling and controlled, both rules. It has following benefits: lightweight, low memory usage, and it has few dependencies. Comparing with other WebRTC realizations, ESP WebRTC consists of less code, and it currently only depends on SRTP modules. Other modules is either contained in IDF or contained in IDF component registry. ESP signaling. ESP signaling provides an interface for signaling realizations. User can customize its signaling realization while if he can use the peer default implementation. We also provide some default implementation for signaling for Google APP-RTC and Amazon KVS-RTC. User can select and combine peer and signaling implementation to suit their real needs, such as it chooses peer default and APP-RTC signaling to build up APP-RTC app. Also, it can use KVS signaling and peer default for Amazon KVS-RTC app. The signaling interface is quite simple, like this. Security. WebRTC provides security realizations. We just realize it according to WebRTC protocols. It provides following security: connection setup using DTLS. Currently, we use embedded TLS to realize it. Peer verification is done using SDP certificates, and the transferred media data is encrypted by SRTP. The data transfer over data channels is over the established DTLS connections. And also, we provide constant freshness to detect peer status, so that when peer is disappeared, it can disconnect it on time. Next part we are talking about is about ESP capture. We develop ESP capture for that. For the protocol part, ESP WebITC, the peer default and signaling realization can suitable for any platform, but there are many device-related things like camera and microphones, and you need to do adaptation for it. We develop ESP capture for user to simplify the adaptation for a new platform. It supports following features. It supports a variety of audio and video devices. It abstracts capture device into common audio source and video source interface. Also, it abstracts audio and video encoders into interfaces. Through this, user can customize source and encoder through abstraction. We support stream out the basic audio and video data. It also supports access stream data into containers like TS or MP4. It supports streaming out the masked data or recording it into local storage. Also, ESP capture supports multiple capture passes for stream data. Each pass can consist of different audio and video codecs. Also, it supports dynamic enabling and disabling of capture passes so that each pass can work separately. Also, we add overlay abstraction, means that users can mix their own UI into video streams. Here is the ESP capture architecture. We named one capture as a capture system. One capture system can have one audio and video source, means one microphone or one cameras, but it can have multiple capture passes. Each pass can have one audio and video sync. We named it audio or video sync, means that it has its own audio and video codecs. Also, we can add marks into each passes. For capture pass, we also provide two default realizations, one simple capture pass and one complicated pass, built up using GMF elements. The simple capture pass only consists one encoder, such as one audio encoder and one video encoder. It can meet most of the needs while it consumes minimal resources. The GMF capture pass typically consists of two passes. Each pass can have almost the same capabilities. The input data is separated into two passes by a copy. The copy only copy the data use the data point so that it does not actually copy data. In the diagram, we can show that audio source goes through rate convert to change sample rate, channel convert to change audio samples, and bit convert to change audio bits. Then it is encoded by an audio encoder and output through the audio sync. This is a typical path. User can add its customized or the existing audio elements into it, such as audio EQ, AEC, and other modules into it. Video capture pass. Video capture passes also, the data can be separated by a copy and transferred through video convert to change the color or the size. Then it can mix with the user overlays, then encoded, such as HRUs 264, then output through the video sync. Now I will show the user scenarios about ESP capture. ESP capture is easy to build up following capture system. Basic capture for raw audio and video data, or the encoded audio and video data. Also, it supports stream out file 7 into local storage. It also supports stream out masked data, such as some protocol may want TS stream data, so it can be streamed out through the masked data. It supports capture multiple passes using different codecs or resolutions, such as one pass is used for stream out using H.264. Another pass can be encoded through JPEG. Also, we support capture camera data while mixing with customized UI, typically like add a time step into it. It supports image capture. Also, using the GMF concept, we can easily add other audio processing elements into the pipelines. ESP player. ESP player is used to play stream data or container data. It is a general player, so we just use it to play stream out that in WebRTC. But it can also used in other areas. It supports abstraction of audio and video decoders and renders, making it easy to adapt to different platforms. Now we can see the ESP WebRTC simple usage. User need only do some basic settings, then ESP WebRTC can be started easily. In diagram, we can show that the user need only to configure audio codecs, video codecs, and video resolutions, including RPS information, audio transmission directions, like whether to send or whether to receive the audio data. For the signaling part, the default signaling only need the room URL, so we just provide a room URL for it. Next is the implementation for the interface of peer default and PSP signaling. After this, we can call API ESP WebRTC open, then ESP WebRTC start to start the WebRTC applications. Now, you can see that on picture there is a KVS demo. We successfully stream out the WebRTC data to the KVS peers. This part is we have also a demo video for IPPA RTC. Now you can watch it. It's quite a simple demo, and the P4 board is connected into a router using Wi-Fi, and we connect in through a mobile phone. You can see that the connection speed is faster, and the peak also. You can notice the video quality. It's encoded, use the hardware encoding, and the resolution is 1280 multiply 960. Also, you can see the encoding effect when we do some motions. The next part, we'll do some comparison with ESP RTC. We already have ESP RTC solutions. The difference is that ESP RTC is based on the SIP protocol, while ESP WebRTC is based on WebRTC protocols. For ESP RTC, currently, it does not support P2P connections. We also did not decided to support it in the near future. ESP RTC uses SIP protocols for signal links, whereas ESP WebRTC can use any signal links. Another difference is that ESP RTC transfer media data in clear form, while ESP WebRTC protect data at different levels, as previously mentioned. The choice, if you want to support P2P connection and also you want to easily build up web applications with a security chaos, I think ESP WebRTC is the right choice. Finally, let me share some debug tips. There are two tips. One is on the platform part, another is on the browser part. On the platform part, you can typically fetch in server log to analyze it. Another thing is that you can also fetch network traffic data using Wireshark and filter user case during different stages. Like when check the network, the connection build up issue, you can use case stun DTLs. And during the media data transfer stage, you can use RTP and RTCP to fill it. Another point is that we provide a PC simulation environment for ESP WebRTC. So you can almost use the same code and reproduce your issue and fast fix for it. For broad part, you can typically inspect and check the console log firstly. Also, you can check the network traffic on the network patch. Browsers also provide a special debug patches for the WebRTC. For Chrome, it means WebRTC internals. You can see the connection build details and the media data transfer details. Also, you can fetch network traffic data as mentioned on the platform. There are also some difficult things. You need to fetch some Chrome logs. You can look at WebRTC logs on the WebRTC logs page, or you can add the log verbosity using the command lines. So this is all the things I'm talking about. Thank you.